Hey guys, how are we doing? So some of you may have just finished your maths with Ronnie. And you're now doing chemistry. Fantastic. So welcome. Hopefully this finds you well, finds you still motivated, still kind of plugging on through your studies and coming to these sessions so we can help you finish the spec. Those of you in year one. So Merrifield World, the diary, Faye, Megan, Benyon, how we doing? How we doing? So pleased that you guys could make it. So hopefully you guys have been spreading the word for us. We want to get as many students as possible coming in here, just continuing their studies, making sure that you cover all of the year one specification. And you know what? We'll do an exam at the end. We'll do an exam at the end. So obviously in the kind of plan that we've got, the schedule that we've got, then that's going to, well, that's outlining obviously exactly what our plan is over the next few months for you guys. You told your peers, but they don't want to revise. Well, yeah, I mean, this is kind of revision, isn't it? But we're doing some learning at the same time. You know, I mean, I think if you just want to, I mean, there's other things you can do if you just want to do past paper questions. But if you want to learn, if you want to kind of get the kind of 101, if you like, on the tips and tricks and my advice on these different topics, then, you know, this is the place to be, isn't it? You know, hopefully over the last few sessions, you guys have learned a fair bit. You know, I've given you kind of like a best of, if you like, over the last few days. So is it buffering for you guys? What is going on? So we are buffering a little bit right now. I'm not entirely sure what the dealio is with that. And just refresh my page, see if I'm still going. So it's all being a bit weird at the moment. I think the reason is that Zoom is going crazy. YouTube is not receiving enough video to maintain smooth streaming. Yeah, so it's an issue with Zoom, I think. Right, I think we're back. Are we back? Is it not buffering now? Okay, well, let's just crack on, shall we? So obviously, I mean, with it buffering, it's a bit of a nightmare. Yeah, so if that happens, you know what, I'm just going to crack on. This video will be here when we're done. Okay, so hopefully, you know, there won't be a buffering issue then. It'll just play the video from start to finish. You know, I've just checked my signal and I'm getting like, you know, I'm on crazy like 400 meg or something here. So I'm thinking it's an issue to do with Zoom. All right, so there we go. Right. Redox, ladies and gentlemen, redox. So I wanted to show you something very quickly. So what I've done, actually, I'm not going to show you in the Exambulance. I have my cheat sheets. Okay, so you go into the top section, useful documents for AQA, OCR, and Edexcel. You can go in there and find your year one cheat sheet. In your year one cheat sheet, you will find, amongst many, many other awesome things, a list of common oxidation states for all the different elements that you're likely going to be using in these redox questions. Okay, so obviously we've got some general rules and stuff. Now, at the heart of redox in year one, the main thing is identifying oxidation states. Okay, so we'll check that out now. So I'm just going to share my screen, and hopefully this will work. And we're not going to have any more buffering issues or anything like that. So I'm going to keep my fingers crossed for that. Okay, so what you should be seeing right now is my blank iPad screen. So yeah, I hope it doesn't start buffering again as well. So we'll see what we go. Okay, so T-Boy, you're just watching Redox before. That's awesome. So redox, okay, oxidation states. Let's do this in a less angry color. So oxidation states. So what we need to be concerned about, okay, is the common oxidation states. They are directly linked, if you like, to the common ions that you get as well. All right. So for example, group one, okay, they've got two common oxidation states. Obviously, elemental, that's 0 oxidation states. But group 1, I use Roman numerals, okay? The reason I use Roman numerals for oxidation states is that it keeps them separate and distinct from charges on ions and stuff like that, okay? Absolutely, we're going to be using oil rig all the time, okay? So group 1 is +1. Group 2 tend to have an oxidation state of +2. 3 tend to obviously have an oxidation state of +3 in their compounds. In terms of group 6, they tend to have -2. Group 7 tend to have -1, okay? Now, there are elements that have variable oxidation states. Ones that you might find that have variable oxidation states, so more than one stable oxidation state, are like almost like mid-P block elements like phosphorus, sulfur, nitrogen, okay? So things like that, okay? So mid-P block tend to have variable oxidation states, okay? What we should actually put down in here is hydrogen. That tends to be +1 as well in most things, okay? And yes, absolutely, Dari, transition metals, okay? So transition metals are also variable too, okay? Now, you don't really deal with transition metals too much in the first year. In fact, hardly at all. That's more of a year 2 thing, of course. But it's worth noting, all right, that transition metals, they are famous for having many kind of different stable oxidation states, okay? Yeah, good knowledge, Dari, on your Roman numerals there, absolutely. Group 4 have an oxidation state? Not really, okay? If we take a look, group 4, they tend to have variable ones like tin. Well, basically, they range between +2 and +4, okay? So +2 and +4, whoops, that's a 4 for group 4. They change in terms of what they prefer to have, but it's either +2 or +4, okay? So I'll tell you what, let's see if we can identify some, I want you to type in, you can use numbers, don't worry about having to use Roman numerals. I use Roman numerals for the reasons I stated before, but let's see if you can identify some oxidation states for me, okay? So I'm gonna give you a species, okay? So it could be just an ion or it could be a compound, and I'm gonna underline an element. I want you as quickly as you can to tell me what the oxidation state is of that element, okay? So I'm going to go, let's do a nice easy one first of all. Let's do the C in CO2. So what's the oxidation state of the C in CO2, guys? So that's the first one. Put your answers in the chat. So once you've done that, the next one is going to be the C in CO. So what's the oxidation state of that? Of course, the previous one, CO2, was absolutely +4. The next one for CO, the answer here, absolutely +2. What about the nitrogen in NH3? So what's the oxidation state of the nitrogen in NH3? Sticking with the nitrogen, let's do NO2, the nitrogen in NO2. Good, it was -3 for the nitrogen in ammonia, absolutely spot on. So yeah, NO2 next up. What's the oxidation state of nitrogen in NO2? Spot on, +4. Okay, so this is +4, this is +2, this is -3, and this one is +4. Now let's ramp this up a little bit. I want you to tell me what the oxidation state of the manganese in KMnO4 is. Okay, so KMnO4, the oxidation state in that for me, please. Okay, so whilst some of you are doing that, I'm going to write another one just because I know there's a lag on this chat. What about MnO2? That is a thing on its own, MnO2. Good. This is +7 oxidation state, which is why it's called potassium manganate 7. So next one, MnO2. Oh, wow, there's a multiple choice. Yeah, they do put these in. Okay, so yeah, +4 is the answer here. Okay, now what about aluminium nitrate? So I want the oxidation state of the nitrogen in aluminium nitrate, please, guys. So we're ramping this up a little bit. So a lot of people saying +1, is that for, no, it's not for the question I just asked. So we got +3, +6, -3, 2, we got +3, we got +3, we've got a lot of different answers here. +5 from Sarah, T-Boy saying 5 as well. Okay. Let me break this down for you. If they give you something like this, you can make life really, really easy for yourself. This, ladies and gentlemen, is an ionic compound. So let's make it an ionic compound. We have Al3+, and we have 3 lots of NO3. What's the charge on NO3? Well, it's 1-, okay? So we explode it, we break it up into its individual components, okay? So we've got Al3+, we got NO3-. Now, all we need to do is just focus on that NO3-. So what is the answer here? Somebody has already put the right answer. So what is the answer for the nitrogen in NO3-? It is +5, okay? Absolutely +5, good. Okay, +5. So we all seem to be pretty on with this, and hopefully that little trick there, okay, when you've got a more complex compound and they're asking for that oxidation state of just one element in there, or you don't need to take into account the aluminium, you're going to end up in a whole world, you go down a rabbit warren then, and it's no good to you. So just take the anion, if you like, and just say, right, well, if we've got that one anion, what's the oxidation state in there? So it really, really simplifies the process for you, okay? So it's 5 because in NO3-, we are aiming for a -1 overall oxidation state. Oxygen takes it down to -6 because there's 3 of them, always -2 oxygen. So then to get from -6 to -1, the difference is +5, okay? Ooh, I shouldn't have put the lines over the plus, but there we go. Okay, that's it, because it's got a 1- charge. So what you have to do is balance the oxidation states of the elements within that compound. Obviously, you're aiming for a flat 0 when it's neutral overall, but of course the overall charge, okay, you need to aim for that when there's an overall charge. Okay, so NO3-, we're aiming for -1. Okay, that's it. So you do have to know like the rules in your oxidation states. Okay. Now, obviously we've seen here that nitrogen is so variable, okay? We can have +4, -3, okay? But in any compound they give you, you will have things to hang your hat on. So there'll be really common elements in there that you're guaranteed you know the oxidation state of, like hydrogen and oxygen, and so on and so forth, okay? So let's take a look at something slightly different. What about ICL. ICL is a compound. Okay, ICL can absolutely form, just in the same way that Cl2, I2, Br2 can form. First things first. Okay, if we had ICL as a compound, it is covalently bonded. What would the dipole be on it? This is my question. It is related. I have got a reason for asking you this. Okay, so where would the negative dipole be? Which one would be delta negative? It'd be a permanent dipole, but which one would be delta negative? That's my question to you, ladies and gentlemen. Good. The chlorine is delta negative. The reason, because it's more electronegative. Okay. So why am I banging on about this? What is the point of this? Okay. So the I will be delta plus, the Cl will be delta negative because it's got a higher electronegativity. So if you get a compound with 2 nonmetals, okay, the negative oxidation state is always attributed to the most electronegative in that compound, okay? Always the most electronegative in that compound. So bearing that in mind, if chlorine is the most electronegative, in this case, chlorine would be -1. Iodine would have an oxidation state of +1. Okay, in this particular compound. So you can get weird ones like this where you need to figure out, right, what's got the negative oxidation state here? Okay, what's got the it's closer to fluorine, absolutely. It is more electronegative. We talked about electronegativity yesterday, Sakura. So if you want to check out yesterday's year 12 live, then absolutely, by all means, go ahead and do that. And I tell you all about a trend in electronegativity there. So when you've got these weird ones, and you can get these weird ones, you always give, when you've got a non-metal compound, you always give the most electronegative one the negative oxidation state. If ever you're wondering which one it is, okay, then you give the most electronegative the negative oxidation state, and then the other one the positive oxidation state. Okay, so that's really, really important that you know that, because they can, you know, it is tricky. It is tricky. Okay. Now, I'll tell you what, identifying oxidation states is one thing, but identifying oxidizing and reducing agents is another. So let's take a typical example of disproportionation. Okay, so let's say I added chlorine to some hydrogen bromide. No, not hydrogen bromide. Let's not do that. Let's do some potassium bromide. Okay, there is a typical displacement reaction going on here, where you end up with Br2 and potassium chloride. So you're going to get two of those, and that's our typical displacement reaction. Okay, but what's actually going on here? Can somebody identify for me, please? Okay, the chlorine does displace bromine. Can someone identify the oxidizing agent for me, please? What's the oxidizing agent in this reaction? Big T saying chlorine. Chlorine's a stronger oxidizing. Yeah, absolutely. Okay. So remember what we said yesterday in terms of trends. In the halogens are oxidizing agents. Okay. The halides are reducing agents. So this is, I'll tell you what, I'll change color. Oxidizing agent. Okay. Now, specifically, ladies and gentlemen, what's the reducing agent? What's the reducing agent? Good, absolutely, the Br. All right, so this is, well, specifically, Benion's got it. The Br minus is the reducing agent. Okay, so the oxidizing agent is chlorine. The reducing agent is bromide. Okay, bromide. And the way you can tell this, all right, oxidizing agent. Now, whenever they ask you this question, what's the oxidizing agent? All you need to do, and I think somebody said this in the chat, is look for what's being reduced. Okay, so oxidizing agent, excuse my rubbish writing today, equals the species that is reduced. And the opposite is true. The reducing agent equals the species that is oxidized. Okay, so it's really, really a really simple method. Okay, when you read a question that says what's the reducing agent, all you need to do, you want to flip it in your brain and go, right, well, that's basically saying what's oxidized. So bang, you've got it. Okay, so it's much easier to think about what's reduced and what's oxidized, as opposed to what's the oxidizing agent and what's the reducing agent. Okay, so make sure you write that down if you haven't heard that before. Okay, so if you're looking for an oxidizing agent, look for something that's being reduced. Boom, you've got it. Okay, in terms of reducing agent, look for something that's oxidized. All right, so that's the simplest method I can give you for identifying those. Now, a really common question is obviously these displacement reactions. Okay, another way is the oxidation states increase. Yeah, absolutely. Okay, so I was just going to go with that. So one thing to remember, okay, so if something's been oxidized, that means that its oxidation state has increased. Okay, so it's gone up. Okay, if something is reduced, and this is where it really makes sense, that means its oxidation state has decreased. Okay, and reduce and decrease, well, they're kind of synonymous, aren't they? Okay, so oxidized, that's where the oxidation state has gone up. And then reduced is where the oxidation state has decreased. It's gone down. You've reduced it. Okay, so that's where those where those names come from. So the colors. Okay, so basically, if you've got Cl2AQ, that's very pale green. Okay, so if you've produced some Cl2, okay, aqueous, then it's very, very pale green. If you've produced some Br2, that is yellow orange. And if you've produced some I2, that's brown. Okay, so those are your color changes for your displacement reactions. Okay, not cream, because they're tests for halide ions, aren't they? They're tests for halide ions. They're no good to you. All right, they're no good to you. So we're going to come back to our halogens in a little bit. All right, we're going to come back to our halogens in a little bit. What I want to talk to you about is an oxidation states decrease for oxidizing agent. Yeah, because the oxidizing agent has been reduced. Okay, so that's why I was saying here that if something has been reduced itself, i.e. an oxidizing agent, that means its oxidation state is going down. Okay, so let's break this down. Let's think about what's actually going on in terms of electrons. Okay, so identifying them, yeah, absolutely. So in terms of electrons, what's going on? So let's say we do have this Cl2 plus potassium bromide gives us bromine and 2 potassium chloride. Okay. If we take away the spectator ions, if we take away the ions that aren't getting involved in the redox at all right, and in this case, it's the potassium. So the ionic equation is Cl2 plus 2Br minus gives you Br2 and 2Cl minus. That's what's really going on here, okay? Really going on here. So chlorine's reacting with the bromide ions, obviously oxidizing it and then being reduced itself. So if we broke this down into what's really going on, and I've seen these questions quite a lot, is in terms of electrons, what's happening to, all right? So we can say that the chlorine, okay, what's happening to the chlorine here? Well, the chlorine is actually being reduced. So it's gaining electrons. So 2 electrons goes to 2Cl minus, and the 2Br minus are being oxidized. So they are going to Br2 and 2 electrons, okay? So these are known, of course, as our half equations, all right? And those half equations are really important to help you understand exactly what's going on with redox, okay? So, of course, this is oxidation. No, it's not. It's reduction. And this is oxidation. So being able to break these down really helps, okay? Spectator ions don't change from left to right. Absolutely. So if I did this in green here, so our potassium here is K plus. So if you're looking for your spectator ions, they're the ones that don't change in oxidation state. So K plus, and it's still K plus over here. So nothing's changed. So you can eliminate those completely. And that's where you end up with your ionic equation. Okay, they absolutely, Sanan. They remain the same state and oxidation state. They're spectator ions. You can take those out, and that's how you write your ionic equations. And then you can break down your ionic equation into your half equations here. Okay, your half equations. Now, I want to come back to halogens because for AQA and EdXL, identifying redox states, we started with that, Mohammed. Okay, we started with that. So I want to come back to halogens because for AQA and EdXL, obviously you guys need to tackle the dreaded reactions of sodium halides with conch sulfuric acid, okay? So what we need to do is, before that, I want to talk to you about oxidation and reduction in organic chemistry, okay? So electron affinity is the nth change of one. Yes, that is very true. And we'll be talking about that in the next hour, Ryan, all right? I want to talk to you about organic chemistry. What are our oxidizing agents in organic chemistry, ladies and gents? Not in this video, no, because it's for year 1. It's for year 12, isn't it? Okay, we don't do redox titrations in year 12. So what are our oxidizing agents? H2SO4 is a really good oxidizing agent. You're right there, Miss C. Absolutely. But yeah, not necessarily. It's not something we use in organic chemistry, is it really? Okay. Nitric acid, no. Ah, good. The dowry, K2Cr2O7. PCl5, no, I wouldn't use it as like to oxidize alcohols and stuff. Good. So we got two, haven't we? We've got acidified KMNO4, and we've got acidified K2CR2O7. No, Siri, I don't want to know anything. Thank you very much. Okay. They've got to be acidified. All right. And we use them, generally speaking, in organic chemistry at AS, we use them for oxidizing primary and secondary alcohols to aldehydes and carboxylic acids for primary, and to ketones for secondary. Okay, so that's what we do. Now I just want to go into this for you because I think it's really, really important. All right. What happens if they're not acidified? Well, I'm going to break this down for you. So if these are oxidizing the alcohol, what do you suppose is actually happening to these reagents themselves? If they're oxidizing agents, what's happening to them? Yeah, they're reduced. Absolutely. Okay. So KMNO4 gets reduced. So what we can say is that, you know, again, let's ignore our spectator ions just for a minute. Let's call that MNO4 minus, and let's call that CR2O7 2 minus. Now, this is really important to help your understanding of this, is that when MNO4 is reduced, it gains electrons, right? Okay, so it's gaining electrons, and it actually goes to make Mn2 plus, okay, and something else. What is that something else that's created, do you think? What is that something else? It's gaining electrons, it's being reduced, so we got the Mn2 plus. Good, it's water. Absolutely, it's water. Now, when you've got oxygen and you're taking oxygen away from things or looking to add oxygen to something, in a half equation like this, because we've got electrons flying around, water is always the key. So whenever you see oxygen, you think, right, well, it either gets turned into water or I need some water to add oxygen to it. So what else we need? What else do we need in order to make our water? Well, that's hydrogen, and it comes in the form of hydrogen ions. Good. So these are hydrogen ions on the left-hand side. Okay, hydrogen ions on the left-hand side. So we've got 4 oxygens here, so that must mean we make 4 H2O. Now that, ladies and gentlemen, is the reason why we need 8 electrons, 8 hydrogen ions. Okay. Good, Sanan, I'm pleased. Okay, so that's why we need 8 hydrogen ions. Now, I'm going to get back to the question before about what happens if it's not acidified. But so this is the acidified bit. That's where all our hydrogen ions come from hydrochloric acid or sulfuric acid or something like that. And Raseb, my next question was absolutely that. How many electrons do we need? Okay, so this is oxidation, alcohols and things. Okay, alcohols. So how do we find out how many electrons we need? Well, we rely on our skills that we were talking about earlier in the tutorial, okay? The oxidation state of the manganese here is +7. We said this before, right? It was one of the questions we did before. You could balance the charges, absolutely. Over here, the manganese, the thing that's being reduced, is now +2. What's the difference? Well, the difference is 5. Let's not forget, ladies and gentlemen, that in terms of redox, if it's gone down in oxidation state, if it's been reduced like this, if it's been reduced by 5, it's literally gained 5 electrons, okay? And that's something that not a lot of students think about. So when you've got a change in oxidation state, literally, that means it's gained 5 electrons. So that is our balanced equation for the reduction of the manganate. Okay, now it's not year 13 stuff. I always teach it in year 12 because I think it's really important you guys understand what the heck is going on with these oxidizing agents. Okay, the color change, incidentally, anybody out there got a color change for it? Purple to colorless. Absolutely, it is purple to colorless. Okay, so let's do the same quickly with our dichromate because it does the same job. Cr2O7 2 minus. That's also been reduced. We are going to need some hydrogen ions, and we get Cr. What do we get? Orange to green is dichromate, yeah. What are we going to get here with our CR what? And we are going to get H2O here. It's CR3 plus. It's CR3 plus. Okay, so we're going to get 2 of those. So how many waters are we making? Well, that's got to be 7 H2O because we've got 7 oxygens over here. Okay, we've got 2 chromium ions, CR3 plus. So there we're going to need 14 hydrogens. Okay, our dichromate. Okay, minus 14, so that's plus 6 here to plus 3. So how many electrons do we need? Plus 6 to plus 3. Think about this carefully before you answer. T-Boy, you got it. It's 6 electrons, and Sanan as well. 6 electrons. The reason is that, yes, chromium is going from a plus 6 to a plus 3 oxidation state, but let's not forget there are 2 of them. Okay, so we need 6 electrons in order to do it. Okay, so in terms of copper, that's a completely different set of equations. That's redox titration. We're not going to touch on that here because it's for year 12. But I just wanted you guys to understand what goes on. And I know that I believe AQA and Edexcel need to know about writing redox equations in acidic conditions. And this is acidic conditions, or an examples of half equations in acidic conditions. Okay. So what can I explain again, Miss C? The bit about the chromium. Well, the chromium has gone from plus 6 to plus 3, so it's been reduced. So you need 3 electrons per chromium atom in order to reduce it. Okay. So that's why, because there's 2 chromium atoms, we need 6 electrons to do it. So 3 would do one of them. You need 6 to do both of them. And because it's CR2, that's your answer there. Okay. Is that okay with everyone? So the reason it's acidified is, the way I see it, to give the oxygen somewhere to go. You need the hydrogen in there in order to create the water. So you need the hydrogen ions in order to do that. If there's no hydrogen ions present, if it's not acidified, the reaction cannot take place, which is why it's so important that when they say, right, what oxidizing agent you're going to use to go from ethanol to ethanoic acid, it's acidified potassium manganate or acidified potassium dichromate, because if you don't write that acidified, it doesn't work and you won't get the mark. Okay, so that's why. So the water's not acidic. Well, you put some sulfuric acid in there. It's usually sulfuric acid we use. A few drops of conc sulfuric acid to supply those hydrogen ions, and that's all it is. Okay, so you'd literally have your ethanol if you were doing ethanol. You'd put some of your dichromate solution in there, potassium dichromate solution, and you'd add a few drops of conc H2SO4 to supply your hydrogen ions, and that would be it. Okay. Yeah, so balance and combining half equations is something that we really need to do. Absolutely. Okay. Now. So that's just a little insight in terms of redox for year 1, in terms of what you're going to require this for in terms of your organic chemistry. Okay, Raseb, I went through that, mate. You're going to have to rewind and listen to it again. I've done it twice now. You do OCR and your teacher didn't go into too much detail. Yeah, well, I think for me personally, I mean, I spent ages developing the TT course. It's bang on specific for the exam boards. Okay, so AQA, OCRA, and Edexcel. Now, there are a handful of videos there at certain points where it's not mentioned in the spec. Maybe you wouldn't have been taught in school, but they're in there to help your understanding. So that's where you pick up those A star and A marks, okay, by understanding the bones of this and how this works. You could just, remember off by heart some equations to get you through, but that doesn't mean you understand it. So I've put some of these videos in like this, and why I wanted to talk to you about it today, to help your understanding of what's going on in terms of these reactions. Now, we talked about color changes. Now, the color change has got nothing to do with the alcohol or the aldehyde that you're oxidizing here in terms of organic chemistry. It's got nothing to do with that. It comes with the change in oxidation state of your transition metal in here, okay? So Mn in this format, in a +7 oxidation state, this is purple. So the MnO4 is actually purple, and the Mn2 plus is actually colorless. Okay, so it's the reduction of that transition metal in this reagent. That's what causes the color change. And for your Cr2O72 minus, this is in the +6 oxidation state, it's actually orange. And in the +3 oxidation state, it's green. Okay, so that's what causes your color change. That's what causes your color change. Okay. Yes, Rasev, I haven't forgotten about that. Okay, so the electron bit is the hardest thing. Yeah, it is. It is. Writing these half equations. And you know what? In year 2, you're going to be doing a lot more of these. And I know some of you are in year 2 here, so you know. Right, so like I said, AQA and Edexcel, you do need to know the reaction between sodium halides, so solid sodium halides, and your conch sulfuric acid. So if you guys are OCR, I apologize, but you know what? There's no harm in you listening, because we are going to talk about the basic concepts of redox and stuff like that, okay? It is kind of linked to the where you need to know the titration. Yeah, I think those half equations are so handy. In year 2, you must remember those half equations for manganate, dichromate. Oxalate is another one that's really, really important, and thiosulfate. So those 4 half equations, really important to remember. So I'll say those again one more time. The manganate, dichromate, oxalate, which is C2O42 minus, and the thiosulfate, S2O32 minus. Those 4 half equations, remember them, because they're going to dig you out of a hole when you get to an exam question. I promise you that. Okay. So yes, this bit I'm going to go through now is AQA, and all I'm going to do is outline the equations and the observations. And it's just a memory game, this, an absolute memory game. Okay. So this is NaX solid plus conch H2SO4. All right. So this is what you need to remember. On one page, this is everything you need to remember. Okay. So I'm just going to blitz on through this. So if you're OCR, then no, you don't need to remember these, you lucky people. All right. So if we've got sodium fluoride, and tell you what, let's remind ourselves. Which of those that I've just written down the right-hand side is the strongest reducing agent? Which is the strongest reducing agent? F minus or I minus? I'll give you a clue. It's not one that's in the middle. Strongest reducing agent. So we've got a few votes, and the majority has it. Absolutely, is I minus. This, ladies and gentlemen, is our strongest reducing agent. From what we said yesterday, lots and lots of shells of electrons. It's gained an electron from somewhere else. Because of all that shielding, something else comes along that wants that electron. It's like, yeah, just whatever, just take it. I can't hold on to it anyway because of all the shielding, right? So it just lets it go. So it's the strongest reducing agent out there. Let's remember that as we go through this. So sodium fluoride. So NaF plus H2SO4, we do not get a redox reaction, okay? We get hydrogen fluoride and 2 hydrogen fluoride and Na2SO4. That's what we get. Now, some people, they write the equation like NaF plus H2SO4 gives you HF and NaHSO4, okay? So looking at the mark schemes for both AQA and Edexcel, because there's 2 schools of thought here as to what you actually produce, they accept either, okay? So whichever one you remember, okay, that's the one you stick with, all right? I tend to stick with the top one, but you know what? You stick to whatever you feel like sticking to, okay? No reaction. I mean, I did say no reaction in the content guide. I'm looking at changing that because in the last set of exam papers I did, a question did come up and they required you to know it. So I'm in the process of making a change to that video. So I would say there is a reaction. What type of reaction is this? It's not redox, okay? This is not redox. What type of reaction is it, ladies and gentlemen? if it's not a redox reaction. It's not disproportionation. There's no change in oxidation state, so it can't be disproportionation, because disproportionation is a type of redox reaction, isn't it? Good, Sam. It's an acid-base reaction. So the H2SO4 is acting as an acid. It's donating protons. And the fluorine in this case is acting as the base, or the fluoride ions acting as the base, accepting a hydrogen ion. So it is an acid-base reaction, okay? It is absolutely an acid-base reaction. Now, just to save a bit of time, I will also say that NaCl is exactly the same, okay? So those two reactions there are both exactly the same, all right? So if you've got sodium chloride, it is also an acid-base reaction, not a redox reaction, okay? So I'm just going to copy that. I'm going to cheat. I'm going to paste it. Boom, that's not redox either, okay? If you said neutralization, yeah, I think, no, it wouldn't be neutralization. I would always refer to it as a acid-base reaction, okay? Yeah, good. Well, Aisha, hopefully that's a good thing. All right. These are pretty intense, but we're dealing with 45 minutes, in which case, actually, we have spent 45 minutes so far. So I got 5 minutes to go through this last bit. So why are they just acid-base reactions? Because these are not strong enough reducing agents to reduce the sulfur in sulfuric acid. Okay. They're not strong enough. All right, not strong enough reducing agents to reduce the sulfur. However, when we get to bromine, NaBr, it is, okay? And there's two reactions you need to know. You do get sodium bromide plus H2SO4 gives you hydrogen bromide and Na2SO4. I'm just using the top reaction like that. So you do get that reaction the same as the other two. You get that acid-base reaction, all right? But you also get a redox reaction. So for me, that is 2Br minus plus 2H plus plus H2SO4. In fact, what we could say is this. The 2HBr that you've just produced plus another H2SO4, that gives you bromine, sulfur dioxide, and 2 water. So it's a second equation that you're going to get. Okay, so 2HBr, H2SO4 gives you Br2. So just think of it like a follow-on reaction. Okay, like a follow-on reaction. So what are your observations here? Observations are massively important. I'm going to do these in purple. So this is actually an orange solution or a brown gas. This, how do you describe SO2? It's basically a colorless gas. Okay, so that's another observation there. Okay, so really, really important. They love their observations. Okay, is the second one a neutralization reaction? No, this is actually a redox reaction. Okay, so this reaction here is a redox reaction. Okay, doesn't HBr act as a catalyst? No, because it can't be considered a catalyst because it's actually reacting. Okay, it's actually reacting. Catalysts remain chemically unchanged in the reaction. That is not true for HBr. Okay, so lastly, we have got NaI. This is where it gets interesting. Okay, so in fact, I can't use all that. So we've got 2NaI plus H2SO4. That gives you 2HI and Na2SO4. That is the same as the other three. Okay, so all four of them have this acid-base reaction. Okay. So we get a second reaction, which you know what is exactly the same as the bromine one. So you get 2HI plus H2SO4. That gives you I2, SO2, and 2H2O. So it's exactly the same as the bromine one. Exactly the same as the bromine one. Okay. But then because iodine is a stronger reducing agent, it can actually reduce sulfur even more. I should have said actually in this last one that sulfur here has gone from +6 to, oh no, wrong one. It's gone from +6 to +4. Okay, so it's gone from +6 to +4 there. It's been reduced by 2. All right, been reduced by 2. And iodine does that, and that's fair enough. But it takes it even further. The difference between acid base and neutralization is where we produce water, a salt and water. We haven't produced that here, okay? So I'm not over my 5 minutes. So because iodide ions are an even stronger reducing agent than bromide ions, they actually get to reduce sulfur even further. So what we end up with is 6Hi reacts with H2SO4 even further to produce 3I2, sulfur, and 4H2O. So you can see here in these reactions, I use green again, we've got sulfur being +4. Here, sulfur is 0. So the iodide has reduced it even further. Okay, even further. Yellow sulfur, absolutely, it's yellow. Good. So you get a yellow solid, all right? And then the thing is, it's that good a reducing agent, it can reduce the sulfur even more. So what we end up with is another one, 8Hi plus H2SO4. Okay, so 2, 6, and 8. Remember 2, 6, 8. That gives you 4 iodines plus H2S plus 4H2O. Okay, so all of those are redox reactions. The oxidation state of sulfur is now -2. Okay, I would say yes in terms of memorizing it. Okay. Oh, thank you very much, Mimi. Yeah, so these are really, really simple if you just think about like, okay, what do I need to learn? So let's just highlight these. I'm going to use orange because it's not a color I've used yet. So sodium fluoride, well, and sodium chloride just have one reaction. It's an acid-base reaction, and all you need to do is remember that. The bromide ions, okay, the bromide ions also undergo that acid-base reaction, but they're just about strong enough reducing agents to reduce the sulfur from +6 to +4. Okay, think of it that way. The bromide ions are just strong enough reducing agents to reduce the sulfur from +6 in the H2SO4 to +4 as SO2. Okay. In the NAI, it does the acid-base reaction. It also does the same redox reaction as bromide ions, so you get the SO2, but it goes 2 steps further. So you've got 4 reactions for the iodide, okay? So in terms of observations, let me just highlight these. Observations, this, okay, the hydrogen halide that you get in all 4 of these reactions, those are white fumes, okay? The SO2 is a colorless gas, okay, that you get with the bromide and the iodide as products. The iodine, incidentally, you could say that was an orange solution or, a brown solution or a purple gas. You can say purple gas, okay? Purple vapor, good. The sulfur is a yellow solid, okay? You could call it a precipitate, I suppose, but it is a yellow solid. And our H2S, that is a pungent gas. That is a rotten egg smell gas. That is nasty, absolutely nasty, okay? So that, ladies and gentlemen, is redox in a nutshell. Everything you need to know. So in terms of breaking it down, what do you need to know? Well, you should be able to identify oxidation states, okay? In fact, I'm going to stop sharing now. If I can. Oh, it does seem to have frozen, which is really weird. Why is it frozen? Anyway, guys, if you're still listening, then something's gone wrong. And I can't seem to do anything. So what I'm going to do is I'm going to bid you farewell. I'm going to see you tomorrow. Okay, we're going to talk about some bonding, mainly I reckon about shapes of molecules and IMFs, because they probably seem to be the trickiest thing. So I'm going to outline once and for all exactly how to identify polar molecules and therefore the intermolecular forces between them, and so on and so forth. Okay, so that's what we're going to be doing tomorrow, and I will see you then. Take it easy.